This video discusses the use of transfer functions. A transfer function uses a linear system. So if you have a nonlinear system, you have to first you have to basically make a linear approximation to that. The transfer function has some nice properties because what it can do is it can actually you can look at a transfer function to determine the steady state value, and you can also use it for performing stability analysis, and you can also use it for time domain functions, and so you can do step responses and that sort of thing. So basically, if we have a system, so I'm just going to kind of, okay, here's my system, which is in the box. Here's my system. And if we're going to force it, okay, so we're going to apply some kind of forcing function. And what we want to do is we want to look at how is this system responding. So X is the position or the response of the system due to the forcing function. And so basically what we do with the transfer function is most of the time we are going to assume that before we apply the forcing function that the system is at rest. So the system's not moving. All right, so now we just did a simulation with the bungee jumping. Okay, so I just want to maybe start out by discussing that. So here we have the bridge, and we have a bungee cord attached to the bridge, and we had our bungee jumper jumped off, and so he's jumped off here and he's bounced around, and now he's just sitting down here, hanging down here by his feet, not moving. Okay, so he's already bounced out, and here was like the original length of the cord, but of course because he's hanging on it now, it's stretched out. So he's sitting here, he's not moving anymore, he's done bouncing around, and he's just hanging there. So let's say that he actually has a fan. So let's give him a little battery operated fan here. And when he turns on that fan is going to pull him down further than what he already is. All right. And so the response then, that fan, when you turn on the fan, that would be our forcing function. Okay. So turning on the fan is our forcing function. So that's going to be a step increase. Okay. And let's just say that, normally we refer to this as a unit step. Okay, so we have a unit step, meaning that it goes up 1 unit, whatever your particular units are. So let's just say here that if the tension in the spring, whatever the tension in the spring is, we're going to say the square of the tension in the spring is the amount of force that this battery operated fan is going to bring down. And so what's going to happen then when that fan is turned on, so it was off here, and then here we'll call this time t equals 0, we turn on the fan. And so what's going to happen, it's going to pull him down. Now remember, we described down as positive, but it's going to pull him down further because the fan's pulling him down, but it's actually, as he goes down, he might bounce around a little bit. And we'll get into with the transfer function whether we can tell whether he's going to bounce around when he does that. All right, so our system, remember that the acceleration, which we describe as x double dot, okay, so, a lot of times we use, I discussed that before, x dot dot of t is the second derivative. So a lot of times you might want to write that as more in the traditional format like this, okay? But inside of MATLAB, I'm just going to use the variable xdd for x double dot. So this is my acceleration. All right, and so we already looked at that, right? According to Newton's laws, right, the acceleration, or when we apply a force to an object, right, the force is equal to the mass times the acceleration. So the acceleration is basically the sum of all the forces divided by the mass. Okay, and so when we Okay, so the acceleration, right, that's our second derivative. So that's like x double dot versus t. That's our acceleration. And we know from Hooke's law that that the acceleration is going to equal to the sum of all the forces being applied divided by the mass of the object. And so to make life easy in this case, let's just say that the mass is equal to 1. Okay, so that we have the mass is equal to 1. And so if we were to write this then, right, we would have the second derivative, d squared x of t dt squared. So the second derivative, which is our acceleration, okay, so I'm also just kind of referring that to like x dd. So that is equal to Hooke's law, right? We've got Hooke's law, which is kind of the spring effect within there. So that's going to be minus k h for Hooke's law times the distance of the stretch minus the friction, okay? And now remember, we have to use linear friction here, so I'm just going to use a linear form of friction. So I'm just going to say this is the friction coefficient. Kf is the friction coefficient. Now this coefficient, would have to do with, what kind of clothes the jumper's wearing, and, and what, what the area of the jumper is, and all those sorts of things. Times the velocity, right? So the velocity is dx dt. Right? And then we've got the forcing function of the fan that the user is using. So we have this forcing function. Now the forcing function, what I'm going to do, I'm going to scale it. It's going to be a unit step. We turn the fan on, but I'm going to scale it based on the spring constant of Hooke's law here of the tension there, just to make it nice and neat. We could use a different scaling factor if you wanted. You can make it twice that, or half of that, or a tenth of that, whatever, but I'm just going to use that for right now. So that's going to be my forcing function. My forcing function is a unit step times this coefficient here. All right, so now to do a transfer function, what we're going to do is we're going to take this. This is what we call a differential equation, right? This is a differential equation. It's got derivatives in it. And so this is describing how the acceleration is changing with time. Okay, so this is time domain. It's telling us how the system is changing with time. And so what we can do is we can convert this into the frequency domain using what's called the Laplace Transform. Okay, and the Laplace Transform, just a simple description of it, if you have a derivative such as dx dt, then we take this to, like I say, basically the frequency domain. So we use a variable s, okay, and s basically refers to j omega, where j is the square root of -1 and omega is the radian frequency. So it's in radians per second. So it's the angular frequency, which is in units of radians per second. And so it's s times x of s. So what we do, we use a capital X here, and it's a function of s now. It's a function of frequency. All right, now, so when you do the Laplace transform of a derivative, you get s, which is this j omega frequency piece times x in the frequency domain minus the initial condition. So minus x of 0, which basically represents the initial condition. Now, as I already said, we're going to assume that the initial condition is 0. And so we basically, if you take the derivative, you just get this s times x of s. And if you take the second derivative, which we have over here as our second derivative, right, you would just get an s squared times x of s. So what I'm going to do is in this equation now, I'm going to apply the Laplace. Okay, so we're going to perform Laplace. Okay, and again, we're assuming all initial conditions are 0. And so therefore, this is a second derivative, so this gives us s squared times x of s. And that is equal to Hooke's law here. So when you do the frequency transformation here, you get minus kh, because this is Hooke's law coefficient, and this is just a scalar value, so nothing happens to that, but the x of t becomes x of s. And then we have the friction term, right? This is the first order linear friction term that we're using. And so we have this friction coefficient. Again, that's just a fixed coefficient times s times x of s, because there's a derivative piece there. So that's that s. So anytime you see an s in a Laplace transformation, that's telling you that that's a derivative piece. And then we have our forcing function, which we have to move the forcing function now into the frequency domain. And as I said, I'm just multiplying that times Hooke's law again. And then we just take that into the frequency domain. So that's just f of s here. All right. Now, what we're going to do, right, is we have this system, right? So here's my system, and on the left side is my forcing function coming in. That's my input, and x is the output. Okay, so now if we do that in the, so the transfer function is what's in between there. So you have f of s on the left side and x of s on the right side, and so whatever you're left with is your transfer function. So I'm going to solve this equation for x of s divided by f of s. All right, and so whatever's left is my transfer function, and a lot of times they actually write a capital H of s to represent the transfer function. Don't have to use that, but a lot of books you'll see, textbooks, you'll see that in there. So we're just going to solve this now. So I'm going to move all the x's over to the left side. So that gives me s squared x of s plus k of h times x of s plus kf s times x of s. And that's all equal to my k of h times the forcing function. Right, so now we can factor this out. So we get x of s times s squared plus, and I'm going to put the s here, so it's plus kf, my friction piece. So this is my friction piece, times s plus my Hooke's law coefficient, right? And then that's equal to the Hooke's law coefficient times my forcing function in the frequency domain. And then again, I want to solve for x of s divided by f of s. So divide each side by f of s and divide the left side, or both sides, by what's in the square brackets here, the s squared plus kfs plus kh. And so that's going to give me my transfer function, x of s divided by the input. So this is the output divided by the input. All right. And so that's telling me what is the box doing. All right. That's the transfer function, is transferring any input into whatever output response that that system does. And so that's going to give me this K of H divided by the S squared plus my friction piece times the first derivative plus the KH. So remember, S represents derivatives. Okay, but it also is representing the frequency response here. K of H. All right, so this then is my transfer function. This is a second order because it's got S squared in there. All right, so this is a second order transfer function. It's a second order system. Okay, so anytime you're going to have any oscillations, you must have at least a second order system. If you have a first order system, okay, a first order system, the response is going to, like, when you apply a step, it's just going to go up very slowly and eventually level out. That would be a first order system. Okay, so this would be a first order response or a overdamped second order response. So what do I mean by that? Well, remember, your damping is your friction, right? Well, that's what's going to slow you down. So let's take a look here now. If I had, see, one of the nice things about transfer functions is because they're linear. Let's say that I had a system like this, which was S plus omega n. Okay, and then I fed that out, the output of this first system, into a second system that was identical. Okay, so I end up, because this is linear, we can actually do this, and these would just multiply. So I would end up getting S squared plus 2 omega n times S plus omega n squared. Okay, all right. I'm sorry, I wanted a omega n. That was the denominator down there. So this, I get an omega n squared, and this is the denominator. So so in each of those boxes, sorry, I just wrote the denominator piece in the box, but in each of the box I have omega n divided by S plus omega n. And so when you multiply those together, in the numerator you'll have omega n squared, and in the denominator you get S squared plus 2 omega S plus omega n squared. All right, so now if you look now at these two, right, these two basically have this exact same form. All right, now what I called omega n there, omega n is what we call the natural frequency of the system. Okay, this is the natural frequency that it's going to oscillate. So if you do have oscillations, this would be the frequency that you would oscillate if you had no friction in the system. Okay, so if Kf, your friction piece, was 0, then we would oscillate at the frequency of Kh, the square root of Kh, right? So, because if you look at this, K of H, Kh, which was the Hooke's law coefficient of the bungee cord, right? That's equal to omega n squared. So that's equal to the square of the natural frequency. So if you take the square root of that, that would give you the natural frequency of oscillations of this system. All right, now the actual oscillation frequency will change when you have friction in there, which of course you'll always have some friction. So it will slow down the oscillation some. That frequency will slow down, but it'll be near, it'll be relatively close to that natural frequency, depending on the amount of friction at least. Okay, so if you don't have a lot of friction, it'll be very close to omega n, that natural frequency. All right, so but remember, this term here is the term with the velocity, right? That S represents your first derivative, which is friction term. So this is basically your friction coefficient. Okay, this is my friction coefficient. So 2 omega n basically says that the system is critically damped, and so if when I turn on the fan, I'm going to go down to my final value and stop without bouncing. All right. So if your friction coefficient here, okay, so if Kf is equal to 2 omega n, then that is what we call a critically damped system. And the system will not oscillate. It'll go down to the final value and then stay there with no oscillation. If Kf is greater than 2 omega n, then you have even more friction, and the system is going to be overdamped, which means it's going to be a very, very slow system, and it'll look almost like the original system. So there'll be no oscillations. So if it's critically damped or overdamped, no oscillations. But if Kf is less than 2 omega n, what that's going to mean is that it's going to come up, it's going to oscillate and bounce around, and then eventually it's going to end up at that value. Okay, so this is what we call an underdamped response. So we can tell that if we have a second order system. Now this actually only works for a second order system, because if you have a third order system, it's going to affect it some, so your values will be shifted some more. But if you have a second order system where you can simplify this system down to an approximate second order system, you can tell what the natural frequency is. You can tell whether you're going to have an underdamped response with oscillations or an overdamped response, or if it's going to be basically critically damped by looking at this transfer function. The other thing you can tell is the final value or the final distance that it moves. Okay, the final steady state value. SS for steady state, the final steady state value. And you get that by letting S go to 0. So if you let S go to 0 in your transfer function, right, this is S squared, so you get 0 squared. And you have 2 omega n times 0. So these two terms go away. And so what you're left with would be omega n squared divided by omega n squared. And so your final change then would be you would move 1 unit, whatever your unit is. So like with the bungee jumping, our unit was meters. So that means that when our jumper here, when our jumper turns on this fan, that fan would pull him down, and he would be 1 meter down further than what he was before. Okay, using the values of the coefficients that I use. So that was kind of why I chose. That was kind of why I chose that the step response be KH. Okay, and that made it there. But if the step response was only 1/10 of KH, right? So it would be, 0.1 times KH divided by KH, right? And so then we would only move 1/10 of a meter. Okay, so we can tell all of that by looking at the transfer function. Okay, so that's one reason that we like transfer functions. We can tell whether the system is going to bounce around or if it's going to be some kind of slow overdamped response. We can tell how far, what the final distance or the final output is going to be. Okay, all that can be told from the transfer function. Okay, and we can also just tell whether the system is going to be stable. All right, and so we'll talk about that next week when we do a root locus. But you can tell whether the system is stable. Right now, I can tell you that the system is stable because the roots of this are negative. Okay, and so I can tell that. But when we close the system, we can still tell whether the system is going to be stable or not. So we can do stability analysis with that transfer function. Now, if we wanted to simulate this using Euler's method, right? So if I said, hey, here's my transfer function. So I have h of s, I have some forcing function, f of s, and f of s is going to, and I want to know how far is this going to move me. So here's my transfer function, h of s, and h of s was equal to, right, what we had there, h of s was equal to kh divided by s squared plus my friction term plus kh, right? That was my transfer function. So if we wanted to simulate this using Euler's like we've been doing in the other labs, right? All we got to do is cross multiply and change back to the time domain. All right, so I'm basically just going to reverse what I did. All right, so this is saying that x of s divided by f of s is equal to my system here, right? And so I cross multiply. So that's going to give me s squared times x of s plus kf s x of s plus kh times x of s is equal to kh times my forcing function. All right, and then I can switch this back into the time domain. So that's going to be, d squared x of t divided by dt squared, my acceleration, plus the velocity term. So that's going to be dx of t dt plus my spring term here, kh times x of t is equal to kh times the forcing function in the time domain. So now we're going to solve for the acceleration term, right? So we got d squared x of t dt is equal to minus my friction term minus my Hooke's law term plus the forcing function. All right, and then if I wanted to put this inside of octave, of course I would have my for loop. Of course you got to do your initial conditions, but you'd have your for loop where you would have k is equal to 2 times the length of t. All right, and then you would have your second derivative. So I'm going to write that in terms of x double dot, and step k is going to equal to this term, so that's minus kf times x dot of k minus 1. I'll use my previous value for that. And then the Hooke's law piece of this was x dot here, make sure I can see that d well, times the x of k minus 1, right, plus my plus k of h times my forcing function at k minus 1 step, right? And then we would integrate. So we would have to first integrate the acceleration to get the derivative. So this would be x of d, the first derivative, the velocity term, at time k, or at step k, is equal to x of d of k minus 1 plus your time step times your x double dot at step k minus 1, right? This is just Euler's here, all right? And then that would give us the velocity term, and then we would calculate the position term. X at time k would be x of k minus 1 plus the time step times the first derivative, x of d at time k minus 1, right? They're just using simple Euler's integration. So these are my integration pieces, and then of course we would end the for loop, right? So this is taking, so I took the transfer function, right? So I took the transfer function and cross multiplied and solved for my x and my highest order derivative here. So you're solving for your highest order derivative. You evaluate that, right? You evaluate your derivative, and then you integrate all the other values. It doesn't matter whether it's a second order, which I've got here, a third order, fourth order, fifth order, or even a first order. First order is just a little bit easier because you would just have evaluate the first order derivative and then integrate once. Okay. If it's a third order derivative, then you're going to have 3 integration terms there. All right, so let's just kind of review again. The thing about a transfer function is that we apply the Laplace transformation, which takes it from the time domain into the frequency domain. And to do that, we have to have a linear system. Okay, so it can't be a nonlinear or chaotic type of system, or if that's what you have, you'll have to approximate it down to a linear approximation. And then nice things about this is we can find the steady state value, and we can find out various things about the stability. And when we get into root locuses next week, we'll know even, we'll see what we can do to determine if we try to apply controls to the system and how that affects our stability using what's called the root locus. So the transfer function is a representation of a differential equation, right? An equation with a bunch of derivatives in it. And it's a representation of that in the frequency domain.